All right, well, as I tried to give you on the title, there's this idea out there that solar thermal is dead. And I'm not going to get into an argument on that in detail, but I do think that the work that we're going to do during the rest of the semester is going to show that that statement is short-sighted, maybe based on some misinformation, some lack of information, and also a lot of government incentives out there that are based on the same. In any case, to get out why it is that people would we think about that, we can take a look at the two water heating alternatives we have so far. So what I'd like you to do to start out, please, no need to copy this down, but I'd like you to take a look at those two pictures and see if you can really quickly describe for yourself what's going on. So you might want to pause this. This is the first picture right here. What is that a picture of? A method for water heating, and what are some of the symbols? You might want to pause it and check yourself. And then how about this alternative over here? What is that a picture of, and what are some of the numbers like? What's actually going on? So in any case, hopefully you've paused and take a look at it. Let's take a look at this one right here. So this is basically a batch water heater. We're going to have a box. We're going to have it filled with water. This might be a cold water inlet. During the day, we're going to have solar hitting that surface. That surface, we want a high solar absorptivity and we want a low emissivity so that much of the solar that's coming in is absorbed and hardly any comes out by emission. Then we'll have hot water at the end of the day. And then in a typical efficiency, well, it varies. We did a spreadsheet for that and we found that there's a lot that goes into it. But a good water heater, we can get somewhere above 50% efficiency, maybe 55% efficiency. Certainly some people are going to claim more, and with some assistance by whoever's running the batch collector, you can get upwards of 60% of this solar energy into the water. Okay, this second picture here, this would be the alternative to solar thermal. This is taking solar energy and making your first step, boom, we're going directly to heat. Okay, and this would, of course, would be PV. Our first step is going to take solar and make it go into electrical. So we're going to have electrical energy going like that. Okay, so this is a PV generator. We're going to get a charge separation. And if we hook it up, we're going to get a charge flow. That's a resistor that's put into a hot water tank. And as the electrical energy flows around like this resistor converts it into heat, and the heat flows into the water. If we size this properly, make this generator large enough, pick a resistor that gets us close to the maximum power for production for this PV cell, then we could do pretty well, and we could have this tank of water end up being hot water at the end of the day. Okay, what was the efficiency like? Well, we've got two steps in this case. We have we have sun energy converted to electrical. That's this step here. And then we have electrical energy converted to heat. And unfortunately, the efficiency is not great. This first step, a typical efficiency would be about 15%. Of course, you can do better than that. And there are some people who would say that's ridiculously low. But if they're going to make it if they're going to go from that low number to what they claim is a more reasonable number, it's going to be something like 18% these days. So that's not that far off. And then this step is really, really good. The electrical energy that gets in there, hardly any is going to come out of these wires, and we're going to get about 98% efficiency. So put those two numbers together, and you've got pretty close to 15% efficiency. So, hey, a lot of people are going to argue that for the advantages here. First of all, this is just wire that's going in and out of your house, whereas in this case here, you're going to have piping that's going to need to enter the house. And there are some more complicated systems out there. Nonetheless, we want to be able to do better than that. So let's go outside and start talking about what is an alternative that actually takes this here, which is about 15% efficient, and can make it better than this here in some people's minds that's 55% efficient. So as we talked inside, water heating, we're not going to do it with resistance heat. Just to try to give you a visual on this again, I got this solar panel, sun's hitting it, so we're creating electrical energy, and we can put that electrical energy through a resistor like this. Okay? And that resistor is going to turn that electrical energy into thermal energy. It is getting hot. If I touch this here, I can actually feel it warming up. One way we get surface temperatures is we use these guns. and they actually give us a pretty good reading on surface temperature. And I can see it's actually going up. It's going up about a couple degrees, every little bit. And this is eventually going to get so hot that it's going to be hard to touch. So then what would we do? You'd want a water tank, but if you were trying to warm up some water, just to give you a visual, we could go ahead and do this. We're not going to do this, but we could go ahead and take this resistor, we could put it in there, and then we could put the water in there, and that would warm up our water. And our efficiency was really, really low with that. Less than 15% of the solar energy coming and hitting this panel actually ends up that water. So how are we going to do better? We'll talk about that for a few minutes. So what we got here, is we have electrical energy, and that can power a resistor, or it could also power a motor. So what we could do is we could get what you could call a thermal energy grabbing machine, a free thermal energy grabbing machine, and run it using this power. Those free thermal energy grabbing machines have a motor in them. So basically what we would do, I have one over here, we're going to go over and take a look at it in a minute. I would actually use this and hook it up to my leads, and I would run this extension cord over to where that machine is and use this solar power that's turned in, this solar energy that's turned into electrical power to run that machine. So let's go take a look at that real quick. All right, go ahead. Yeah, so try to ignore what we got up here. This is our solar dryer, very high efficiency. But this is our free thermal energy grabbing machine. You can call it a heat pump. Here is the power from the heat pump and to the heat pump, the electrical power, and it's a pretty large circuit. It takes a lot of electrical energy, so it would take a much bigger PV panel than what I had out there to run it. So how does this actually work? Well, we can't open it up and get inside it, but over here, basically, these are, where my finger's running, those are fins, and those fins are connected to piping, and that piping has refrigerant running in it, And we turn this machine on, that refrigerant is going to probably be in the teens, 15 degrees, 16 degrees, And it's next to air out here, and right now it's about 55, 60 degrees out here. So thermal energy in the air is going to flow naturally. It always goes from high temperature to low temperature, out of the air and into that refrigerant. And that's free thermal energy. I'm not paying anything for it. And so then we got the energy in the refrigerant, and the question is, how are we going to get the energy out of the refrigerant and into the water inside? When the thermal energy is in the refrigerant, then what the refrigerant is going to do is run through a compressor that's driven by a motor, And as you guys know about compressors, what compressors do is increase the temperature of a vapor, and they also increase the pressure of the vapor. So right when that refrigerant that I was referring to is still pretty cold, even though it's picked up thermal energy, but the compressor in here is going to be able to bump it up to 180 degrees, 190 degrees, etc. And then it's going to run into the house through a refrigerant line that's like this, and it goes into the house, and then that refrigerant goes through a water heater, and it's, it doesn't mix with the water, it's actually in an enclosed tube, and then the heat comes out of that 180, 190 degree refrigerant and goes to the water, And then once it goes out of the water, it actually ends up condensing, or as the refrigerant goes through the water, that refrigerant pipe goes through the water, it ends up condensing, and it comes back out here as a liquid, and then goes back into this machine, and the process can repeat itself. So, the name for this machine is a heat pump. So this would be an air to water heat pump. A regular pump takes water and raises it from low elevation to high elevation. A heat pump takes thermal energy and raises it from low temperature out here, and then coming out here it's at high temperature, and then we can end up delivering it. So that is another great alternative to think about, and that is to use a PV panel, which creates electrical, to run one of these machines. And the California Energy Commission right now is really big on that. They really feel that's going to solve a lot of our energy problems. Great. Okay, so now I got the heat pump on, and we got this fan on top. Some of the electrical energy is going to run this propeller fan, and I can feel the air coming up here. Down here, it's sucking that air in across those refrigeration coils. So we've got like 55 or 60 degree air coming across the refrigeration coils. The refrigerant is pulling thermal energy out of that air, and then that thermal energy is going into the water heater in the house. All right, so in short, people who say solar thermal is dead are saying, look, let's going to do this alternative instead. We're going to get a free thermal energy grabbing machine and use it. And that is the heat pump. So the heat pump is the machine, and we're going to power it with PV. So this PV generator is going to create electricity, and that electrical input is going to run the heat pump. All right, so what's the heat pump going to do? It is going to grab thermal energy from somewhere, okay? Just by the nature of how it runs, it's going to grab thermal energy from somewhere, and then it's going to take that thermal energy and it's going to move it somewhere else. So, as I was trying to say, probably sorry about my hand. As I was trying to say outside, a water pump takes water from low elevation to high elevation. A heat pump is going to take thermal energy from low temperature to high temperature. All right. So this would be a low temperature and this would be a high temperature. And then with some sort of configuration, we can get that temperature delivered where it wants to. Okay, so the heat pump that I showed you outside, it is taking thermal energy from air. And that may be worth a quick reminder. So bear with me while I try to get this configured. So it's going to get a heat pump like the one I had outside is going to get thermal energy from air. And so to get a feel for that, we go to A17E, one of the main tables you use during your time. A17E from the thermo book. And let's take a look at 500 Rankine. So I'm looking down here for 500 Rankine. So you can see, you can find that 500 Rankine is right there. Okay, why that temperature? Well, if you do the math in your head, 500 Rankine is 40 degrees Fahrenheit. And let's take a look at the U column, 85. So what does U stand for? U stands for internal, or we can basically think of that thermal energy. So that says that 40 degree Fahrenheit air has 85 BTUs in it for each pound of air. And that's energy that's just there. It's outside. If it's 40 degrees outside and we want to heat our water and heat our home, if we can somehow grab some of that 85 BTUs per pound mass, that is free energy that we can use. So the following is worth being able to do. If you're working with a client and proposing heating alternatives, you might say, hey, there's electric resistance, we can do some solar thermal, we could use a heat pump, and it might be worth being able to give them a bare bones explanation of what a heat pump does, and that's what the thermo book does in chapter 6, which you can take a look at. This diagram here represents the entire machinery, no details, an overall view of what it does. And what we're going to say is the heat pump does is it's going to pull energy from some sort of source. The source that we were talking about outside is outside air. And that energy is thermal energy. The book's symbol for that, the thermo book symbol, and a similar symbol is used in the solar book, is Q. And they use subscript L because we're pulling it from a low temperature source. Okay, we're going to take that heat and we're going to deliver it to some sort of end use, like heating water or heating a house. And that's Q as well, QH. Okay, how does it do it? We need some sort of input. So here we have electrical energy input, and that's usually it. That's some sort of electrical energy input. We could call the energy input E for general energy input, but almost all heat pumps are driven by a motor, and a motor does work, so that is characterized as work. Okay, so that is a schematic of a heat pump. How is it actually going to work? Well, among different things that you should understand is a heat pump follows conservation of energy. So remember I had 85 BTUs earlier, 85 BTUs per pound mass of air. Let's say this heat pump pulls up 85 BTUs, okay? Well, it's going to take some work. I'm just going to make up a number, okay? Let's just say that the amount of work it takes, and work can be in joules, or it can be that can be converted to BTUs, is 100 BTUs, okay? Well, that energy, these two energies are flowing in, and at steady state, energy in is equal to energy out. And so the heat delivered to your source, to your end use, be it water heating or home heating, etc., is going to be 185 BTUs. So there is a diagram that would allow you to explain to someone who doesn't know heat pumps what it does, and it also gives us our first equation that for a heat pump, QH, the heat it delivers, and that can be a total, BTUs or a rate, is going to be equal to the free heat it pulls plus the work input. All right, that's the first part of it. All right. Second thing to think about a little bit is how actually does it go about doing that? And you can copy this diagram down, but the diagram that I'm going to put out there is not really going to be part of this course too much, unless you pick something related to a heat pump for your final project. So I would just think about it a little bit more. How is it actually going to end up, how do we end up going doing that? And of course, this diagram is central to ME128. Yeah, come out of ME28, you're supposed to understand that really, really well. Okay, well, basically, what we're going to do is I'm going to draw some black lines, and that's going to represent piping carrying refrigerant. So we have some refrigerant, and let's put the air over here like this. So this is the air we're going to pull the heat from. Okay, and so this line represents refrigerant moving along past the air, just like it was outside. Okay, and this refrigerant's going to be really, really cold. Really, really cold. Let's say I'm going to make it 20 degrees Fahrenheit. Okay. So as a consequence, because that refrigerant is so cold and colder than the outside of air, and you can get refrigerant that gets down to negative 10 degrees Fahrenheit so that you can operate a heat pump like this up in Lake Tahoe, the heat's going to flow out of the air, thermal energy is going to flow out of the air and go into it. So you can think about there basically like being this blob of thermal energy now. Quick reminder, this is an evaporator and the refrigerant evaporates, it goes through. When during evaporation is oftentimes a constant temperature process. So at this point, the refrigerant now has more energy, but it's still 20 degrees Fahrenheit. Got to bump it up in temperature. What's the ordinary way to do that? We take that refrigerant. So now again, this is piping and the refrigerant's still moving along. You think of this blob of refrigerant moving along, and we're going to have it go through a compressor. And outside, I wish we could have taken the heat pump apart outside so you could see that compressor, but that is a pretty big device. And the compressor there is the largest energy consuming device in our house. It beats the electric dryer, it beats the microwave, etc. It's the largest one. And so basically this compressor is going to be able to compress that refrigerant. That takes electrical energy, so that's where the work is done. By the way, this was QL. All right, and compressors bump up the temperature. So this refrigerant that comes out is going to be very, very high temperature. Let's make it something like 170 degrees Fahrenheit, which for refrigerant in this application is actually quite low. It's going to be a higher temperature. All right, well then what we're going to do is we're going to take that heat that's in there. So this blob of energy, this blob of refrigerant, pardon me, it has picked up heat here and now it has heat. It's really cold here, picked up heat here. Now it's picked up compressor heat. Okay, I'm going to change colors. So now it's picked up compressor heat. And what we're going to do is we're going to take this piping, okay, and we're going to have it go through a coil that is in a water tank. And all this is sealed, and it's the job of the manufacturer to make that those lines are really, really sealed. Okay, and then as it goes through there, the heat is dumped. The heat is actually dumped, all right? And so that blob now has lost its heat, and QH, didn't leave enough room there, QH has actually gone into the water. All right, and then the last step, when it comes out here, it's still pretty warm temperature, but then that's that step with that throttling device or expansion valve, where it drops in temperature and pressure and gets back to this 20 degrees Fahrenheit. What drives the refrigerant around, makes it do this cycle? It's the compressor. It's the compressor. So that is the vapor compression cycle. You all are mechanical engineers. You are the ones in our society that understand some of the main energy consuming devices in our world. Those devices would be things like internal combustion engines, various types of power plants, and in the top 5 is this cycle here. This cycle here is called the vapor compression cycle, and it is part of heat pumps. All right, well, how efficient is this process? What if we pick a heat pump for heating, in particular water heating? So just a quick reminder, this is supposed to be a picture of electric resistance heating. It's not like the electric resistance heating is vertical. It actually comes in the side. You can see that if you take apart a water heater, or if you go to Home Depot and look at the elements, they screw into the side over here like this. But how efficient is this? Well, the efficiency here is basically the energy that we would send to this point, and we would compare that to the amount of energy that we get into water. And typical is upwards of 98%. So really high efficiency. Okay, how efficient is this? We're going to put energy in, And we're going to compare the energy that goes to the hot water to the energy that goes in, and that's going to give us our efficiency. So let's just take a look at a commercial heat pump out there. And the Energy Commission, which is, many people say, is a great place to work. They are certainly incredibly influential, and California is considered pretty much the most energy efficient state in the country, and a lot of it's due to the Energy Commission. Well, the Energy Commission loves this heat pump. Okay, so loves this heat pump. Some things about it. So this would be the tank that would be in your house if you go with this heat pump, and this is the outdoor unit. Okay, where the evaporator is and the compressor is, etc. And there's the fan, like the fan that I talked about outside, and the refrigerant would be running through there and picking up heat when it's running outside. Okay, why does the Energy Commission love this? First of all, it uses carbon dioxide as the refrigerant. You guys, one thing that hopefully you'll study a little bit in ME 128, or if you do some HVAC work, is just what a huge issue refrigerants are for our society. They really cause damage to the atmosphere in a variety of different ways. Well, carbon dioxide is just already in the atmosphere, and we pull it out of the atmosphere and we use it. There's no damage at all. So first of all, the Energy Commission, in my mind, rightly, is very supportive of that. The second thing is the efficiency number. So if you take a look at it, you can't really see very well, but if I get that energy efficient there, it says 4 times more efficient than traditional electric water heaters. 4 times more efficient. So let's do the math. Let's do the math and see how that would turn out. Before we do the math, let me just say that is a little bit of an optimistic number. It's 4 times as efficient under certain conditions, but let's give them the benefit of the doubt. Okay, let's say that they're comparing to a so-so electric resistance water heater in 0.95. Okay, let's go ahead and get the efficiency of this. 4 times 0.95. Shoot, I ought to be able to do that in my head. I'm thinking that's an efficiency of 3.8. Okay? So what does that mean? That's an efficiency of 380%. Well, that actually is physically possible for a heat pump. Basically, that is going to be a ratio of the heat that gets delivered to the electrical input. And that means that if we have 1 unit of electrical input, we're going to have 3.8 units of heat delivered. And that is actually not uncommon. In my experience, a efficiency of 2.8, 2.9, 3, 3.1 is much, much more common. But this organization, Sandin, has been able to certify that their heat pump under some circumstances performs with this COP, so they get to put it on the advertising scheme and no one can sue them, and they say that's all good. All right, that's a little bit weird. Hopefully you remember that, though. Efficiency greater than 1. So hopefully you remember that from Engineering 124. We call the efficiency of a heat pump or a refrigerator or an air conditioner the COP, the coefficient of performance. And the coefficient of performance is a ratio of the heat delivered to the work. And let me just write that down really quickly. This would be a pretty complete picture of a heat pump. If you could actually understand this picture and explain it to yourself or others, you're in good shape. A heat pump pulls free heat. Sorry, this is a little bit. Pulls free heat from some sort of source, air. There are water source heat pumps. There are ground source heat pumps. Then it takes electrical input to run the compressor, and it delivers the combination of the free heat and the electrical work to the end source place, to where we want it to. It can go to heating water. It can go to heating air in your house. It can go to heating a swimming pool, etc. So heat pumps. All right, and then our other equation is QL plus W is equal to QH. So maybe take a second to make sure you've got that down. I want you to be able to do some problem solving with that. All right, so we're going to try to put it together and do some problem solving. So I would like you to, freeze this example and get as far as you can. After I describe it really quickly, I'm going to go out and work piece by piece, so you can try a part and then check your work versus mine. So let's just say, again, we have a family that is super conservative when it comes to hot water. They're going to get by with 20 gallons, and they start the day with 20 gallons of water at 60 degrees Fahrenheit. They are going to use the heat pump alternative. So they spring for a meter squared PV system with efficiency of 15%. that PV system is going to power a heat pump with COP 2.9. So in my estimation, a more reasonable number compared to the values on the stand-in advertisement. Okay, HHI is 14,570 BTU, same value as we used for the previous examples. A, let's just draw the system with the heat pump so you could explain it to a client. Here's an option. Make the heat pump just a circle with the letters HP in there, not with all the details about the compressor and the evaporator, the condenser, the throttling valve. Okay, B, what is the heat pump input over that day going to be? Remember, HHI is the total for the day. C, how much energy actually goes to the water in BTUs? All right. Of the energy that goes to the water, how much is free? And maybe where does that energy come from? And finally, bottom line, what is the water delta T for the air? Again, we were hoping to get maybe like a 70-degree delta T so that we would have 130-degree water at the end of the day. All right, again, encourage you to try to work piece by piece, and I'll be doing the same. All right, well, here's my answer to part A. This may not look to engineering, but in my experience, this is part of engineering. Try to get in some sort of drawing that a client you can work with and explain to a client, a coworker, etc. So, 14,570 BTUs, that's HHI, that's the daily horizontal irradiation, and we're going with a horizontal PV panel for right now because we don't know how to do tilted panels. We'll work on that later in the lecture. Okay, then that electrical energy ends up flowing into the heat pump, and the heat pump can grab free energy, I didn't put that in there, and it's going to deliver heat to the H2O. All right, so that's parts A. It might have been helpful if I had shown the free energy, so maybe I'll show the free energy like that. That's QL. All right. And then part B asked us to come up with some numbers, and that is to come up with a heat pump input. So what is the energy flow going in this case here, if we imagine the energy flow going this way like that? What is that energy flow into the heat pump? And go ahead and work on that. All right, so here's the next part. What is this energy flow that's going to the heat pump? Well, the PV panel takes a percent of that and makes it into electrical energy. The efficiency of a PV panel is the electrical energy produced divided the ratio of the electrical energy produced to the solar. So the electrical energy is going to be equal to the 0.15 times the solar, and I got 2185.5 BTUs over the course of the day that goes that way. And that is essentially electrical energy that does work. So that's going to be the work. Okay, the next thing that we were trying to figure out is actually, this is what we want. How much energy actually ends up going to the H2 over the course of the day. Okay, so basic heat pump problem solving from chapter 6 of the thermo textbook. We got two equations that have QH in it. Here's our COP equation, and there's our conservation of energy equation. So this is looking pretty promising to get QH, okay? And if you think about it, we know work. Work is basically this number right here. That's that work input to the heat pump, but the problem is we don't know QL. We don't know the free heat. How about this equation here? Well, we've got COP, we've got QH, we've got W, and so we can get QH. So just rearranging it really quickly, I'll just do the work right now. Okay, the heat delivered is going to be equal to the COP times the work. The COP is 2.9, so we can just take that number that we just worked out, 2.9, and we get about 6,338 BTUs. Okay, so that's looking pretty good actually, 6,338 BTUs. That's that number right there like that. Okay, and if you have a pretty perceptive client, they're going to say not bad. 14,000 input from solar, and we get 6,000 going to the water. Overall, in a sense, the efficiency of this system is getting pretty close to 50%, a little bit less than 50%. Okay, there was two more questions left. How about the free energy? How about this QL? Well, you can see that QL plus W has to equal to QH. There's a total of 6,338 going that way. This number right here, I could put in the picture, is the 2,185.5. So this is the difference right here, which must be somewhere in the 4,000s. So I'm going to try to get that myself. So 6,338 minus 2,185.5, and I'm getting 4,124 basically. Pardon me, 4,152. Pardon me, 4,152 BTUs. Okay, 4,150 BTUs, not bad. So this is energy we don't pay for. This was energy in the outside air if it's an air source heat pump, energy in like lake water if it's a water source heat pump, energy in the ground if it's a ground source heat pump. All right, how's that actually going to do then as far as our tank delta T? We were hoping for like 130 degree water at the end of the day. So just to remind you of that. Okay, we can do the delta T of any object that does any system that does not change phase by doing the change in energy divided by MC. Well, it's change in energy. This is the change in energy. 6,338 went there. Okay, it is 20 gallons of water, and each gallon of water is about 8.33 pounds. So I can divide it by 20 times 8.33. And the specific heat of water is 1. So I end up getting a 38 degree Fahrenheit delta T. Okay. And so that means that the temperature of the water at the end of the day is going to be, it started at 60 plus 38, it's going to be 98. That's a little bit cool for, particularly if we want to do dishwashing and make sure that our dishes are sanitary after they're all done. That doesn't mean this is a bad system. What that does mean is we need a bigger PV panel to make it work. If you look back at the example from last time, what you'll see is that this number right here is a lot better than PV. With PV, we got hardly any delta T. It was not quite as good as the batch water heater. And that's where there's some argument in engineering that goes into it. Sandin is going to say, look, hey, your professor sold us short. He went with 2.9 for the COP, and we're much better than that. In addition, the batch water heater has some downside. It's kind of interesting to see that's all playing out, and that if you get involved in solar, you'll be involved in these sort of decisions. Okay, good enough. So that's our first part of the lecture today, is taking a look at the alternative that's really being promoted out there, the best way to use solar for heating. The second thing is, regardless of how we use solar for heating, we can do better than we're doing right now, okay? And that is, we are taking a look. All our calculations for solar have been to assume that our panel was horizontal, or our batch water heater was horizontal. And of course, you know, we're going to do a lot better if we tilt it up there. So let's take a look at that as our next step. Okay, so what we have so far is, first of all, that water heating with PV and a resistor is really, really ineffective. You're going to need a huge PV area. We could go to heat pump, and that is out there. But if we took this panel or some sort of a similar arrangement and had it run the motor that powers a heat pump, we're not being as effective as we could be. So why don't you all just go ahead and think for a second about the sun hitting this collector right here, and just remind yourself, is that GHI? So just, we're looking at that collector, is the sun hitting it GHI? Okay, and so the answer is almost. GHI is global horizontal irradiance, and it's the combination of the direct radiation coming from the sun, and you can see the sun's pretty much on me, it's coming down here. There would be a bunch of rays, I'm trying to point at the sun, there would be a bunch of rays coming down like that, and those are all direct rays that are making its way from the sun and hitting that surface. So we got the direct going on there. Okay, what's the other part of GHI? It's the diffuse. So it's the diffuse from the sky. So it's from the stuff from the sky coming over here like this, stuff from the sky coming over here like that. And if my cameraman would just go ahead and sort of sweep around looking at the sky going around here like this, Okay, we don't have 100% clear sky, particularly over there. We got all those trees over there, and they are taking some of the solar that's coming off the sky and blocking it. So we're pretty close to GHI right now. Call it GHI, we're good enough. All right, so how about our arrangement right now that I've got? Maybe a little bit hard to see, but I got the two leads coming out there like that, and if I follow one lead, if I go ahead and follow the red lead, I've got current coming over here like this. It's going through the ammeter and then coming on back. So this ammeter has virtually no resistance, so we're doing I short circuit. And hopefully you can see this. I'm getting about 1.62 amps. Ideally, at 1,000 watts per meter squared, we would get about 1.85 or something like that. That's what the specs are on this thing, 1.85. So we got to be pretty close to 1,000 watts per meter squared. We got to be pretty close to 1,000 watts per meter squared. Okay, let me just go ahead and hold up the book and see if we can remind you something about how these graphs work. So the Grease graph works. So if you take a look at this key figure, okay, it's a really nice graph that shows the performance, not for this PV generator I have here, but another PV generator. And you can see that there are these currents right here, this current on this axis, these are all ISCs. They're short circuit currents. So we've got 1, almost 2, close to 3, 3.7, 4.6, something like that. And each one is associated with a different curve. So you can see basically that the short circuit current is basically, can provide us a measure of how intense the radiation is. The higher the radiation hitting our surface, the larger the short circuit current. So let's just see if you guys can figure it out. Just think for a second. 1.6, I got 1.6. Yeah, I want to do better than that. How am I going to do better than that? I got to have more thermal radiation hitting that surface. You might say, hey, Professor Monty, why don't you wait for a while? Okay, the sun might change position, but really the thing to do is we can make the sun more intense on that surface. The sun right now is coming in at an angle here like this, and quite simply what we want to do is directly face the sun. So I'm going to tilt this up. I can't see, so I'm not cheating. I can't cheat. Hopefully we're getting an increase in current, and that would mean that there's more intense radiation on it. Let me take a look really quickly. Yeah, I got up to 1.9, so I've got some more intense radiation going on there. I might even be above 1,000 watts per meter squared at this point, above 1,000 watts. Okay, so the way it's going to be described, I'm going to go ahead and ask my camera person to move over that way just a little bit and think about the way it's described. The way it's described in your basic PV or solar analysis is what I did was I changed the angle of incidence. So the angle of incidence, we're going to work on that a little bit, is the angle between the normal to a surface and the incident rays. So in this case, I've got an angle of resistance about like that, and it's hard for me to estimate, but it's something like 30 degrees, an angle of 30 degrees, incidence of 30 degrees. Okay, what do we want the angle of incidence to be to maximize our solar collection? Well, we want the sun rays to be as direct as possible on that surface. So what we want to do is tilt this up so that it's direct as possible. So now I had it about like this. The normal's coming out like this, and the sun's rays are basically really, really close to the normal. So we have a very small angle of incidence, and we should be getting some pretty good current. Okay? What actually, if I take it and go to the horizontal, okay, now I'm getting pretty close to GHI, and I have less current. I've got an angle of incidence. And then try yourself to visualize the angle of incidence right now. And it's hard for me to do it. Maybe I'll put it down here, and I can do that really quickly. So what's the angle of incidence? Well, here's the normal to the surface, and the sun's rays were coming over from somewhere like that. That angle of incidence is really, really large, and hopefully we're getting relatively low current. A couple more quick ones. See if you can visualize me holding this so I get angle of incidence of 90 degrees. So angle between the sun and the normal of 90 degrees. Okay? Well, I'm just going to try to do it. It's probably easier for me to stand up. And it looks like it's about like that. My eyesight's not that great or my vision from this angle. So I got an angle of incidence of 90 degrees. That means that the sun is just skimming the surface. The sun's just skimming this surface. And so my guess would be I should get a current of 0. Let me set that up again. So go ahead and check out the current meter and see if we got a current of 0. I'm getting about 2. So what's going on there? Well, the direct radiation is skimming the surface and is 0. But there's still the sky there. There's still that diffuse radiation from the sky, and it's still actually small. Okay, could I do an angle of incidence of bigger than 90 degrees? Well, sure. I would turn it here like this, and let's see if I turn it like this, if I still get any current. And I'm still at about 0.24, and once again, that's the sky over there doing it. I'm going to try to face those trees and see if it goes down at all. So I got this device right here. I got my PD panel, and I'm facing the trees. And it's gone down just a little bit because it's facing less sky. All right, so what we're going to do now is go to the whiteboard inside and see if we can work out the numbers. How can you do computations on that? How can you figure out what is the best angle for your collector over the course of the day to maximize the solar collection? All right, so a new symbol for us. We were outside taking a look at the difference it made, the tilt of our panel, if we got a flat panel versus pointed more towards the sun. And that leads to a new symbol, which is GND, and that stands for G normal direct. So just some quick reminders on some G symbols for solar, okay? Hopefully you can complete this equation. GHI, that's the global horizontal irradiance, is a combination of GDH, which is the direct on the horizontal, plus also we got diffuse on the horizontal. Okay, so we've got this solar coming in on a surface, and we want to do better. Okay, so there's a horizontal surface, and we have this solar coming in. All right, and the idea is, what if we took this surface here and tilted it so it directly faced the sun, so that that solar is coming straight on in? And that's what G normal direct is. So I'll just give it verbally, and you can read about it in the book for homework number 7. But G normal direct is the intensity of solar direct on a surface that directly faces the sun. Intensity of solar on a surface that directly faces the sun. So what I want to do is give you an example that we're going to work through. I'm going to give you the equation for G normal direct in a minute, but I think you're going to understand it a lot better if you can draw up this example. So let me get the numbers on the board. You can be writing it down. So here's our example, some very cryptically. GHI, I'm going to give you GHI. Okay, let's say it's pretty low, 200 watts per meter squared. So maybe it's late in the day. Okay, maybe there's a bit of shade. Maybe there's a bit of some clouds. Okay, G diffuse on the horizontal, which can also be figured out from a weather station data, etc., is 25 watts per meter squared. Okay, alpha is equal to 20 degrees. What is GND? GND. Okay, so let me give that get that problem up there for you. GHI 200, GDH 25, alpha is 20 degrees. What is G normal direct? And I encourage you to pause and do a drawing that represents what's going on with that, and think about how we would go about and doing that problem solving. I'll be doing it quickly myself. Okay, your drawing doesn't need to look like this, but it hopefully would convey something similar. So GHI tells us global on the horizontal, okay? And then GDH is 25, excuse my arm. So that means that the intensity of this stuff right here is 175 watts per meter squared. This is the direct stuff that's coming in 20 degrees. When we say alpha is 20 degrees, that means that's the angle of the stuff directly from the sun. So we have 175 watts per meter squared coming in directly towards the sun. So we're wondering if we actually take this surface and tilt it so it directly faces the sun, how intense is that going to be? Okay, now hopefully you can see there's a bunch of different ways that people think about this. One is you can see that these rays are further spread out here than these rays going directly into that surface. And so that would indicate higher intensity. There's another way to think about it well, as I'll show it in a minute. You certainly could take some time and try to do some trigonometry and figure this out, but I'm going to try to give you a drawing that helps you through it and come up with an equation that's going to give us G normal direct, given that we know G direct and we know alpha. So start with G direct on the horizontal, start with alpha, and end up with G normal direct. Okay, so basically what I've done here, this represents the horizontal, and this is some solar coming in at angle alpha. And we're going to try to do some trigonometry and figure it out. So first of all, what we can do, G is in watts per meter squared. So we can actually think, let's come up with some symbols that represent the watts in the meter squared. So Q, I could say, hey, that represents all this solar that's hitting this surface. And so then G direct on the horizontal would be a ratio of Q to A normal, and A normal is the area of this, pardon me, A horizontal is the area of that stuff right there. Okay, so to help myself out, I'm going to visualize a surface that's perpendicular to the rays. You can probably see I didn't do a great job with this surface. It's supposed to be perpendicular to every single ray, and this would be the optimal surface where we have it going directly in there. Okay, so I'm going to take this triangle here. I'm going to draw it out there and see if I can do a proof where I end up with what G normal direct is. So here we go. This bottom side of the triangle is a horizontal. Okay, and this side right here would be the area of a surface that is normal to the rays. Okay, G direct horizontal is Q over A horizontal. Okay, G normal direct, that's what we're after, is going to be the same Q but over a smaller area, Q over A normal. Okay. So we want to try to plug and chug and do some algebra and see if we can combine that and come up with a formula for G normal direct in terms of G direct on the horizontal. Because a lot of times that's the data that we have. We have G direct on the horizontal, we got to figure out G normal direct. And I think what it just involves doing is trying to figure out in this triangle which angle is alpha. This angle right here is essentially that angle right over there. So that's got to be 90 degrees. So we have a right triangle. If we could just get alpha in there, we'd be in good shape. So maybe pause the video and see if you can find it. Okay, so this is alpha. This is alpha, 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 alpha. Alpha is the angle of all of these rays. So we've got alpha in here like this. So we've got alpha in there like that. So let's try to do a little bit of trigonometry. This is adjacent to, I'm sorry, goodness, I lost my train of thought for a second. This is opposite of alpha. So we could say that sine of alpha is equal to the normal area over the horizontal area. Okay? In other words, we're interested in a sense in what this normal area would be. It's going to be smaller. Okay, and the normal area is going to be the horizontal area times sine alpha. Okay, sorry, that got a little bit low. Okay, so now what we can do is we can put it all together. We can say that G normal direct, so I'm going to take this, I'm going to start with this equation right here like this. Okay, I can say that G normal direct is equal to the incoming solar divided by A horizontal sine alpha, okay, and Q over A horizontal is G direct on the horizontal, and now we've got our equation. So G normal direct, sorry, it's getting a little bit low, but I'll hold it up for just a second, is going to be G direct on the horizontal divided by sine alpha And that is one of our fundamental equations of today's lecture that can be written in just in a couple different ways. So I'm sorry that's getting a little bit messy. G normal direct is G direct horizontal over sine alpha. Okay, let's finish off the problem. So I'll just read it off to you again. We had that GHI was 200 watts per meter squared, GDH was 25 watts per meter squared, alpha was 20 degrees, and we're trying to figure out G normal direct. So go ahead and just pull out your calculator and do that. I'll get the math on the board really quickly, and we should be able to take a look at this and say, hey, what difference does it make actually if we go to a tilted surface? And bear with me for just a second. Okay, there's not a lot to it. Sorry to take up a little bit of time there, but here's our picture basically where we have sun coming in low. Okay, could we take our collector and tilt it up so it's direct? Would it make any sort of significant difference in intensity? Well, the direct on the horizontal is 175. The direct on a surface tilted to face the sun, right towards the sun, would be the direct on the horizontal divided by sine alpha. So I'm going to do 175 divided by sine 20. And I get about 512 watts per meter squared. So we get a tremendous increase by tilting that surface. And that is the start of some pretty interesting work in solar. How much do we want to tilt a surface? What actually makes sense? And we'll keep working on that. All right, so it turns out that directly facing the sun is sometimes not possible or even desirable. And if this is a collector surface, and I end up, the sun's low in the sky and I directly face the sun, that might work out well, but there might also be a lot of diffuse solar that I'm cutting off. In a sense, when I make this completely vertical, I'm cutting off half the sky from actually hitting this surface right here. And so that can make a difference. What we need then is, when we're working with surfaces that do not directly face the sun, we need a measure of how far they are off from directly measuring the sun, and that is the angle of incidence, and your book symbol for that is theta. So just trying to give you I gave you a visual outside, but bear with me, this will be very crude, and then we'll just get to the drawings and the numbers. If this surface were here like this, we're going to say that a solar ray that comes in like this is not directly hitting it. And of course, that makes sense. It's at an angle. How big an angle? Well, this would be perfect. This is direct. This would be 90 degrees. And this would be a bit off. And we're going to make 0 degrees perfect, an angle of incidence 0 to be perfect. So basically what you're going to do is for any surface, you're going to visualize a normal line. That's a line that's perpendicular to the surface. And the angle of incidence is going to be the angle between between incoming solar rays and that line right there. So I'm going to envision an angle between this normal line and the incoming rays. If they're coming in straight from above, angle of incidence of 0 degrees. Okay, really quickly, let's have you guys practice that. What I want you to do is consider the following case. Let's say that the sun's pretty high in the sky, 60 degrees. Beta stands for the tilt of our surface. So a surface that's horizontal would have a tilt of 0 degrees. A surface that is at 90 degrees, so tilted towards the sun, so it's vertical, the vertical surface would have 90 degrees. And if you had a surface that actually faced down towards the ground like that, that would be a tilt of 180 degrees. So beta is the tilt from the horizontal. So I want you to figure out the angle of incidence in this case. And I think it's great to take a minute to just do a quick drawing of the surface, a quick drawing of alpha, and then come up with the angle of incidence. I'll do it the same myself really quickly. And by the way, of course, you want to put the normal line in that drawing. You want to put the normal line in that drawing. Okay, so let's see if we got it. So beta is equal to 0. That means that's a horizontal surface. Okay. Alpha is equal to 60 degrees. That means there's a bunch of sun coming from pretty high in the sky. This angle is 60, this angle is 60, and this angle is 60. There's my normal line. Theta is the angle between the normal line and the incident ray. And so theta in this case is 30 degrees. So we are 30 degrees off from normal direct radiation. Normal direct radiation. Okay, letter B. Let's see if you can give you a little bit more challenge. Okay, so in this one, the sun, it's solar noon. I'll get it for you to look at in just a second. And in addition, alpha is 30 degrees. The sun is lower in the sky. Okay. Beta is equal to 40 degrees. And gamma of our surface is equal to 0 degrees. Okay, so a new symbol for you guys to think about. It's solar noon. Okay, the sun is 30 degrees above the horizontal. Okay, our surface is tilted at 40 degrees, and it is facing 0 degrees. Gamma is the symbol in the book for the direction a surface faces. So I can have a surface that says faces south. That's south this way in this room. That is east if it faced that way. Facing towards you guys, that's west. I could have a surface facing towards me, that's north. So how would we actually picture what's going on in this particular case? Let me just do it with you guys really quickly. The surface faces south. So that's facing south, but it's not tilted at 90 degrees, it's tilted at 40 degrees. So it's tilted at 40 degrees above the horizontal facing south. And in fact, that is a great tilt for collectors here in Sacramento. So I encourage you to try to do a drawing of that situation and figure out the angle of incidence. I'm going to be doing it myself. Okay, here's a start for you. That's the south direction. Okay, this surface right here is not tilted up so it's exactly vertical and facing south. It's tilted up at 40 degrees. Okay, I want to get some rays coming in. By the way, it's solar noon, so the rays are coming in from the south. The sun is somewhere over here to the south, so the rays are coming in here like that. Let's see if we can get those in there. Okay, so my angles may not be perfect, but I got the sun is low in the sky, so I have rays coming at 30 degrees. Some hit the ground and some hit the collector. I only need to show one hitting the collector to figure out what's going on. There it is, and I'm trying to get the angle of incidence. To me, it doesn't look like that ray is straight on. Okay, to me, it looks like if I did a normal line like this, it looks like it's below the normal line. So I'm going to, at this point right here where that ray hits, I'm going to draw a normal line and see if I can do a little geometry and figure it out. Okay, so trying to figure out this angle of incidence. This angle of incidence is this angle in here between the normal line and the sun's rays. Okay. So I'm getting that it's going to be 20 degrees, but let's just check that out. So I took this whole picture here and I tried to eliminate like some stuff, like try to get rid of these other rays. We just need one ray to figure it out because they're all parallel, okay? And I did a sub-drawing essentially down below here, okay? Where this represents the collector or the surface and it's tilted at 40 degrees. This is the ground and this is a normal line, okay? And if I can figure this angle out in here, I'm on my way. And 40, 90, this angle in here has got to be 50. So that angle right there has got to be 50 degrees. And then I got to put this in the picture. Okay, this line right here is basically a horizontal line right here like this. Okay, and there is the normal line. So once again, we got the angle between a horizontal line and the normal line horizontal line, the normal line, to be 50 degrees. So from here to here is 50, so that angle of incidence is got to be 20 degrees. So the answer to this example is angle of incidence is 20 degrees. All right, one last formula for today, and that'll do it. So basically, we're not always going to be able to get normal direct. Some people might disagree and say, wait a minute, there are tracking systems that ensure that our collector always faces the sun, but those are few and far between that are that perfect. So a lot of times we are going to have some sort of non-zero angle of incidence. This G-normal direct we can figure out if we're doing PV or solar design. There's lots of the data available, and we can say, look, I know that normal direct in this case is going to be 275 watts per meter squared or whatever. But if we're going to predict performance and we're going to size panels and we're going to size equipment, etc., we need to figure out, we could call it G theta. Sometimes the book just calls it G. We want to figure out the incident angle on something that's not directly facing the sun. Okay, so what is the formula for that? How do you go about doing that? So basically what we can do is we can use a really, really similar approach where we say, look, let's say suppose we know G normal direct, and let's figure out what is it going to be given this picture right here. What is G theta going to be for a tilted surface given this picture right here? So for the starters, just a reminder, what we did in the past is we said, look, we're going to call this incoming radiation Q. Okay, and we're going to give this an area. So we're going to call this A, and let's see what I did in my notes. Give me just a second, please. Yeah, a little bit of pen work, A normal direct. Okay, so then that's going to be the case that G normal direct is going to be a ratio of the incoming watts to the area. So I'm going to just write that down really quickly so I have that on there. Okay, so then the question is, what if we had a surface instead of facing the sun, did not directly facing the sun? So maybe it's tilted up here like this. Okay, sorry, let me get my fingers out of the way. Maybe it's tilted up here like this. Or more likely it's tilted like this because a 90 degree tilt is pretty high. So that's what I'm going to try to draw in there really quickly, is what if we had a surface actually that was like this, and it captured the same Q. Okay, so hopefully you can see that if I take this very top line, I've got to extend my surface longer. And this surface we're going to say has area theta. So it's going to be an area of our tilted surface. Well, hopefully you can see that this Q here is going to spread out more on these surfaces. I could extend these three lines, and I'm going to get Q spread out over a little bit more over that surface. Okay, so basically our strategy is we're going to try to do some geometry, and we're going to try to figure out A theta. But before we do that, we should actually get our normal line in there. So there's our normal line. And remember the angle of incidence for a surface, so this is a surface right here like this, and an incoming ray is the angle between the incoming solar and the normal to the surface. So there's our angle of incidence right there like that. There's our angle of incidence. And you can probably imagine what we're going to do. We're going to try to draw this circle, pardon me, we're going to try to draw this triangle. It indeed is a right triangle, and we're going to try to put theta in there. So let me see if I can blow up that triangle successfully. Okay, that's one of the incoming rays, and it comes over here like this, and this is that surface that we just had before. Okay, and where is theta in this picture? This angle for sure right here is a 90-degree angle. So let's see, if this is theta, okay, and this is 90 degrees as well over here like this, because this is a 90-degree angle, this is going to be 90 minus theta. That angle in there is going to be 90 minus theta. So we are going to end up getting theta over down here like this. So that's theta. Okay, and if you reason your way through it, that would make sense. Actually, if I take this surface and tilt it up till it's actually normal, then theta is going to go to 0. So that makes sense. All right, what about our areas? This is A theta right here like this. And this is A normal direct. So let's see if we can do the trig. What's the relationship between A theta and A normal direct going to be? Well, A theta is the hypotenuse. So you can check my work. I'm getting cosine theta is equal to A normal direct over A theta. Okay, and now we're on our way. Okay, what were we trying to do for this now? We were trying to figure out a formula for, hey, what's the intensity of the radiation hitting this surface? So that is G sub theta, we could call it, although the book is going to call it G, and I will too myself, but basically it's the intensity of the radiation on our surface of interest. Okay, in this picture here, there's Q. If we actually took this surface and had it changed it to a surface like this, then this Q would come and hit this surface right here. So it's Q divided by A theta. Okay, and then if you do the math, you can see that A theta is going to be equal to A normal direct divided by cosine theta. So let me see if I can get that in there. I'm sorry about this pen. We're going to make it through this lecture. So I'll get that a little closer to you. G theta is Q divided by A normal direct divided by cosine theta. Well, obviously the cosine theta is going to flip up to the numerator, okay, and A normal direct is going to be in the bottom. So let me just write that down, and let's see if I can get one pen to help me out and finish off this lecture. Okay, so there's our next to last step, okay, and then we were trying to relate G normal direct to G theta. This portion of the expression right here is G normal direct, okay? So we get G theta is equal to G normal direct times cosine theta. All right. And that is our last equation before spring break. Before we call it good, let's just check it out really quickly. What if you had a situation like this? So bear with me. Let me just draw in here. It's getting a little bit tough for me to fit everything in. What if I had a surface and the solar was coming in directly into that surface? What is the intensity of the solar going to be on that surface? Well, what is the angle of incidence in this case? It's 0 degrees. It's directly in. So it would be G normal direct times the cosine of theta, okay? And the cosine of 0 degrees, the angle of incidence is 0. Cosine of 0 is 1. So the intensity hitting the surface would be G normal direct, okay? What if we were silly, okay? And we had some solar system where the sun was coming in at this angle, okay? And our surface was actually pretty much parallel to that. Okay, it barely actually comes in and hits this surface at a very low angle. Let's call it 1 degree or something like that, is this angle in here. Okay, so if that's 1 degree, what's the angle of incidence over here like that? The angle between the normal and the incoming rays, that's 89 degrees. So how's that going to work out? The intensity is going to be G normal direct times the cosine of 89 degrees. And if you pull out your calculator and do cosine of 89 degrees, okay, I get 1.7%. So the intensity is going to be very, very low. And this formula, accurately represents what's going on. I'm going to be working on getting several things to you guys. Among them is homework number 7. And homework number 7 will give you practice on the material that we've gone over today. You have everything you need to do to finish off homework number 6. And homework number 7, the first part of it will involve some of this stuff. More information is going to be coming via Canvas announcements. And please feel free to contact me. Please be safe. You guys have a good rest of your weekend.